Today's notes are on the incline plane. Just before we get to that, I want to remind you that most of the time when we have a force at an angle, and this would be the one that is a force at the angle, down here, we resolve that force into its x and y components. So what we do is we take away that Fa and we replace it with Fax and Fay. It's exactly what we were doing in the last lesson. So, a bit of more of the same just to remind you of what we've been doing. So this would be my Fay in this case, and this would be my Fax. And I still have my force of gravity here. So this gets turned into that. What did I do is I replaced this applied force at an angle and I replaced it with my x and my y components, and it's so much easier now. So in this case, looking at this, since there's no friction, when I add up all the forces, and that's what F net means, really I just end up with Fax, don't I? And it goes off to the right. So my acceleration, I can see right away, will be to the right. And I can figure out acceleration. Acceleration is F net divided by mass, right? And so it'll be something to the right, and Fax is the one that's pushing it to the right. Well, what about an inclined plane? An inclined plane is, well, here's an example. It looks kind of like a wedge here. So I have a box, a crate, an object, something on there, and it's on an incline. This is the inclined plane. So we're still going to have a force of gravity downward. So I can draw here, this can be my force Fg here, downwards. Otherwise known as weight, and that always acts straight down. We're going to have a normal force. We're not going to have a normal force upwards in this case, but the normal force is, remember, normal means perpendicular. So if it's perpendicular to that inclined plane, the normal force is actually this direction. A little bit different. And I'm just drawing these from the center of the object. I could draw from the edge of the object however I want. And then the last one, force of friction. If it's present, which direction would that be? Well, I don't actually know what this object is doing. It could have just been pushed up the inclined plane. It could be moving upward up the inclined plane. But let's just say it was placed on there and it started sliding down the inclined plane, in which case the direction that it's moving would be parallel to the plane. It would be moving that way. And the friction is opposite to the direction of motion. So if the object's moving down the plane like that, then the force of friction is going in this direction. Okay, so here I have a couple questions. Which force is making things difficult now? So in the past here, it was this one at an angle was sort of like the difficult one, and once we resolved that into x and y components, everything was kind of cool. In this one, it's a little bit different. It seems to me that the force of gravity is the one that's not playing well with others. If we could make the force of gravity be more consistent with the directions of Ff and Fn, it probably would be easier to add things. My other question is, which direction will the object accelerate? Well, just thinking about common sense, if I have an inclined plane, if I'm going to let this object go, it's probably going to be accelerating down the plane. Okay, so which direction would that be? Well, this line is parallel with the inclined plane. So my answer here is, which direction? It will go parallel to the plane, to the inclined plane, to this direction. So parallel is this kind of symbol here. Okay, so what we can do is we can resolve the force of gravity into two components. We can take Fg here and we're going to resolve it into this one here, which I will call Fg perpendicular. It'll have that little subscript, not a letter but a symbol, so this will be Fg perpendicular. And then I'll have Fg parallel, and I can write it down here, in which case it'll be inside of a triangle, or I can write it over there. I can write it either way. Thinking of it here inside the triangle, I just want to point something out. So here's the angle of the inclined plane, say 30 degrees or 40 degrees, whatever it is. That angle, turns out, it's exactly the same as the angle inside of this triangle over here. So if this long side is the force of gravity, if this side here is FG, which is the same thing as MG, okay, and my 90-degree angle is over here. This is FG perpendicular and this is FG parallel. Let's consider the geometry of how this would work. Well, MG is my hypotenuse and FG parallel is the opposite side. So I'm thinking here that we would use the sine of theta would be equal to the opposite FG parallel over FG. In other words, if we're solving for FG parallel would be equal to FG times the sine of theta, or another way to write it, and I think I have this on the next page over here, FG parallel will be equal to the sine of theta. Similarly, if I go over here and I'm looking at the adjacent side, using cos now, the cos of theta is equal to the adjacent over the hypotenuse, FG perpendicular over FG. And so here I would have FG perpendicular is equal to the force of gravity times the cos of the angle. Or I can write it as, new highlighting, mg. The mg part, that's the same thing as saying the force of gravity. So looking back at my original question over here, just like in my example where I changed FA into FAX and FAY, here what I would do is I would say, well, I will still draw the normal force, and I'll still draw the force of friction, but now I will replace the force of gravity with this one here, and this one is the perpendicular one, so this is going to be FG perpendicular, and this one here will be FG parallel. One thing to note is that the normal force and FG perpendicular will be the same. Will equal FG perpendicular. Why is that? Any acceleration that's going to happen will be parallel with the inclined plane and it won't be accelerating perpendicular to the plane. Just like when I had a crate that was on a surface, even if I was pulling it at an angle, it was not going to be accelerating vertically, it would only be accelerating horizontally. Here it won't be accelerating perpendicular, but it will be accelerating in this parallel to the plane direction. Okay, so let's try a question with actual numbers in here. So we'll go to example number 1. It says a 100 kilogram crate is sliding down a 30-degree incline. So here is our incline, right? This is the 30-degree part. And so this 30 degrees will also be here. And it says if there is no friction, find the acceleration. Okay, so first of all, let's fill in what we can figure out. So I know that the force of gravity is equal to m times g. So that will be equal to 100 times 9.8. So that's going to be 980 newtons. So this one's right here, 980 newtons. There's nothing else that I know yet. I can't figure out the normal force. The normal force is going to be equal to Fg perpendicular. And I do know the friction because it says here no friction, so I can put a 0 here. So I'm going to draw this diagram again. And here again is my 30 degrees. And here is my box there. There's my crate. And I'll draw the normal force just like before. Fn. The friction I won't write in this one. Now instead of writing the force of gravity, I'll do Fg perpendicular and I'll do Fg parallel. So looking at this question, right away I know that Fn and Fg perpendicular are equal and they're going to cancel each other out. So if I want to find the acceleration, is going to be equal to F net over m. And since these two are canceling each other out, it's really just going to be the same thing as Fg parallel divided by the mass. Now Fg parallel, I'm kind of unwrapping my new formula here, is equal to mg sine theta over m. By the way, just how to remember that the parallel goes with sine and the perpendicular goes with cos. You can come up with your own memory tricks, but I kind of look at this and I say, okay, that parallel thing, it kind of looks like a slide, and the word sine also starts with an S. So it kind of works for me. I look at Fg parallel, I see a slide, so then I think that's mg sine theta. Fg perpendicular, it's going to go not with sine, but whatever's left over is cos, mg cos theta. Okay, it doesn't really, you can't do the parallel as kind of like y, because it really depends on the angle. Sometimes it's going to look more like, if the angle is really large, it's going to look more like the y. If the angle is quite small, it's going to look more like the x. So you can't really go with that way, but think of this as a slide. Slide starts with s, so does sine. Okay, hopefully that'll work for you. Continuing on here, we got mg sine theta over m. Now let's plug in our numbers here. The mass is 100 multiplied by 9.8 was g, and then the sine of 30 degrees divided by 100. So I end up getting, well, my hundreds cancel each other out, and I get 9.8 times, now the sine of 30 degrees, it's come up a few times in a little while, is actually equal to 0.5, so I'll get 4.9 meters per second squared. And what direction will that be? Parallel to the plane. Okay, parallel to the plane. In fact, most of these inclined plane questions, I'm pretty happy if you just say 4.9 meters per second squared. That's enough. I'm not too picky about the direction on those ones. By the way, there's a little bit of a shortcut you may have noticed here. This is a special case when there is no friction. When there's no friction, it's only Fg parallel is the only force that's causing the acceleration, because the other two, the normal force and the Fg perpendicular, are canceling each other out. So over here, before I plugged everything in, I could have just gone and canceled out the masses. So that tells me sort of two interesting things. One is, it doesn't matter what the mass is that we put on that slide, right? So I don't know if you remember back in the day in elementary school, you got the big hill, and you got little kids there, and then you got the really big kid, and they're both going to be getting on their toboggan. Well, according to our formula here, if it is completely frictionless, right, if there's not air resistance and there's nothing else related, little Timmy and big huge Johnny, or whatever names you want to pick, they're going to be accelerating at the exact same rate because the mass disappears. It's not even part of the equation. So if it is frictionless, you can see that the acceleration here, the acceleration is going to be equal to, now this is g times the sine of theta. So this is like a shortcut that you can remember if there's no friction. So that's sort of a nice piece that came out of our first one. You see how it worked in this one. G is 9.8. Now the sine of 30 degrees is a half, so that's where the 4.9 came from. Okay, so let's do the second example now when there is friction. And we're going to use friction a 0.3. So, well, I'll just draw the diagram again here. So we've got this inclined plane, and we've got this object here. So we have already figured out that this is Fg parallel. This is Fg perpendicular. This is the normal force. And this will be the friction force. I'm going to draw the friction force a bit smaller because I'm going to presume that it's still going to have a little bit of acceleration down the inclined plane. Well, let's figure out these numbers. Fg parallel is going to be equal to mg sine of theta, which is 100 multiplied by 9.8 times the sine of 30 degrees, which is equal to 490 newtons. So here we've got a 490. Fg perpendicular is equal to mg cos of theta, which will be equal to 100 times 9.8 times the cos of 30 degrees, which will be equal to, do I have the number here? 848.7. Write it in here, 848.7 newtons. Now, looking at the rest of my diagram, FG perpendicular is 848.7, so that means that the normal force is also equal to 848.7, so that my force of friction here is going to be equal to mu times the normal force. So let's find a spot here to do our work. We'll say the force of friction, the force of friction will be equal to mu times the normal force. So that will be equal to 0.3 multiplied by 848.7. So we get an answer of 254.6 newtons. Okay, so we're almost time to finish this. Now we can say the acceleration is going to be equal to F net over m. Looking at my diagram, I realize that FG perpendicular and the normal force are going to be canceling each other out, and that these two are in opposite directions. So I'm really going to have FG parallel 490 minus the force of friction. You know what, maybe I'll write those words out first. I'll have FG parallel minus the force of friction all divided by the mass. So it's very similar to what we had a second ago, right? Over here we had F net over m, we had FG parallel over m because there was no friction. Now we have FG parallel minus the force of friction all over mass. So we figured out that FG parallel was 490 minus 254.6 all divided by 100, and I get an answer of 2.4 meters per second squared, and again the direction would be parallel to the incline plane. Okay, in our last example, example number 3, is a constant velocity. So again we've got a 100 kilogram object, and it's sliding at a constant velocity of 5 meters per second. Well, when you see those words, constant velocity, we should have an alarm going off, a bell saying, oh, constant velocity. That means that the acceleration is equal to 0. That means that the net force is going to be equal to 0. Another way of saying that is that all the forces are balanced. So, looking at my diagram, I think I'm going to override here. Instead of the 45, I'm going to change this to 40 degrees. Otherwise, my x, or my perpendicular, and my parallel are exactly the same, and somebody might just get them a little bit mixed up. Let's figure out what we need to do here. So, again, all it says is fill in the blanks. In most of the other questions, it's what is acceleration? As soon as you see constant velocity, you know the acceleration is 0. So there's not much to do there. So really we just have to fill in the blanks. Well, first of all, the force of gravity is going to be equal to Fg is equal to mg. Get a little thinner pen. So it's going to be the old 100 times 9.8. So again, this will be 980. We should still go and say, well, what is Fg perpendicular? And what is Fg parallel? Because the important thing here is that if everything is balanced, that means that Fg perpendicular is the same as the normal force, which is all our examples have been like that. But as well, Fg parallel is going to be equal to the force of friction. So Fg perpendicular is mg times the cos of theta degrees. So this is going to be equal to 980 times the cos of 40 degrees, which according to my calculator is about 751 newtons. So that means that automatically the normal force is 751 newtons. Fg parallel over here, kind of running out of space for it, so let's do it over here. Fg parallel is going to be equal to mg sine theta, which is equal to 980 multiplied by the sine of 40 degrees. And that is about 630 newtons. So I'll put in a 630 over here. And so that's what the force of friction is going to be, 630 newtons. Okay, so really there were only 3 blanks to fill. That one was pretty easy. This one was equal to Fg parallel, and this one was equal to Fg perpendicular. That's how you figured it out. So for homework, there is an inclined plane analysis worksheet to do, and there are 2 different sublevels 5 and 6 to get from the MOPS. Good luck, enjoy, we'll see you in class.